Okay, so the last talk of this session is by Bhaskar Mukherjee from UCL London, and he'll discuss emergent strong zero mode through local Floquet engineering.
Thank you. Okay, I would like to begin by thanking the organizer for giving me this opportunity to talk here. My name is Bhaskar Mukherjee, and I'm currently a postdoc at University College London. And the title of my talk is Emergent Strong Zero Mode through Local Floquet Engineering. So the talk is about, again, Floquet systems. So the previous speakers has already given a very detailed overview of the field, but for the sake of completeness, I will again go through them very briefly. So again, Floquet system is about time periodic Hamiltonian. So you may have a time independent part, but then you have a time dependent part, which is time periodic, such that the whole thing is time periodic. And then this is the time period, 2 pi over omega. Omega is the drive frequency. And if you are interested only in the stroboscopic times, then everything is governed by this one cycle time evolution operator, which is this time order product, which can be written as like this, where this HF is the Floquet Hamiltonian, which is actually the generator of time evolution in this case. Now, depending on these parameters, which is one is this drive frequency, and you of course have drive amplitude. Then depending on these two parameters, the property of this HF can be very different than this Hamiltonian. And you can have many interesting phases which you don't see if you don't drive. One such example is this irradiated graphene. So if you shine circularly polarized light on a two-dimensional sheet of graphene, then graphene becomes a Haldane-Chern insulator. So for quite some time, there was no experimental realization of Haldane model of anomalous Hall effect, but this thing came out proposing a very useful realization of Haldane model of anomalous Hall effect, which was done in this paper back in 2009, photovoltaic Hall effect in graphene. And then there is also experiment in solid state samples. So bismuth selenide is a celebrated three-dimensional topological insulators, and the Floquet block states and also the Floquet gaps observed in this experiment. These are angle and time resolved photoemission spectroscopy experiment. So the gap observed in this experiment turn out to be matches quite accurately with the gap predicted even from a very simple non-interacting Floquet band structure calculation. So of course you have electron-electron interaction and electron-phonon interaction, which might be very important to stabilize the anomalous Hall effect reported in this case. But even if you neglect all these things theoretically, the gap calculated from a simple non-interacting band structure calculation matches quite accurately with the experimental observation. So that was quite nice. Then another important thing is this Floquet pre-thermalization phenomena, which is also described very well in the previous talks. But again, very briefly, so this time evolution operator can be approximated as like this, where you truncate your Floquet Magnus expansion at some order. Let's say, I mean, if you don't truncate, then the series diverges. So you have to truncate it at some finite order, and that truncated expansion can give you very nice description of your system up to asymptotically long time. Usually we think that in Floquet system, because of this driving, that the time translation symmetry is broken and energy conservation is lost. So that's why you think that system heats up to infinite temperature. But for high drive frequency, where this HFN is still a very local Hamiltonian, so the corresponding energy is again is a very good quantum, can be considered as a good quantum number, and that stops the system from heating up arbitrarily. So this was predicted in this theoretical paper, and also found in this experiment in Bosabat system in 2020, where you can see that this heating time scale, they are growing exponentially. I mean, with the increasing frequency omega. Okay, and then again, another interesting thing is, of course, this Floquet time crystal. So where your Hamiltonian. So for example, if your Hamiltonian have some time translation symmetry, but that's spontaneously broken in the state of the system. But so this thing, so if you take a local observable which does not satisfy, I mean, this unequal sign, so this thing is not satisfied, but I mean, this thing is satisfied with 2T as shown in this figure. So of course, the time translation symmetry of the Hamiltonian is broken. But again, the symmetry, you can see a double symmetry in the time evolution of the system. This was again predicted in these pioneering papers. And here you see long range order throughout the entire spectrum. And it needs, of course, MBL as one of its, as the main mechanism. So by long range order, we just mean that the Floquet eigenstates look like cat states. So where the connected correlation functions never falls. Okay, and then there is a lot of experiment performed in various systems for this time crystal. So one, I will just briefly mention one or two. So this very recent one is in this quantum processor by Xiaomi et al. In this 2022 Nature paper. So in quantum processor, you can apply these unitary gates corresponding to the terms in the Hamiltonian. And then of course you can measure some local quantities and they found that in the suitable parameter regime, in the MBL regime, the discrete time crystal is stabilized by this driving. So this is again a Floquet system, interesting Floquet system. And then this experiment performed. So here you do not have any disorder. So this is a Rydberg atom setup where these Rydberg atoms are just highly excited states of atoms, which you can manipulate using these lasers. And in this Rydberg atom array setup, so this is actually quite well described by the so-called PXP Hamiltonian. So in the undriven case, we have already seen that PXP model shows this car-induced long-lived oscillation, but that's also decays with time gradually. But when you drive with appropriate parameters, they actually found that this is actually a time crystal-like oscillation. So these oscillations period are actually double of the time periodicity of the Hamiltonian. But this happens now only from the nil-like state, like up, down, and down, up, down, up, not from any other state in the Hamiltonian. But this does not require any disorder. So that's the good thing of this thing. So, interesting thing is this happens in a very highly non-perturbative parameter regime, where the both drive amplitude and drive frequency are comparable to the other energy scale in the system. So Floquet is expected to hold, but it doesn't actually. I mean, this is, quite long-lived oscillation. We tried to understand this in this paper. So, and here the only two Floquet eigenstates are cat-like, not all the eigenstates. Okay. But this talk is also about strong zero mode, which was introduced long back in 2001 by Alexei Kitaev. So if you have a P-wave superconducting chain described by this Hamiltonian, which you can decompose in Majorana fermion using these things, and then in the ordered phase, where you have ferromagnetic order, these things are equivalent to some spin model by Jordan-Wigner transformation. And then for the choice of parameters which leave the system in the ordered phase, you see that you have unpaired Majorana fermion at the end of the chain, but on the disordered phase, the Majorana fermions are all paired. So, an important question was, is this thing stable against interaction? So in this interesting paper in 2011, they did some very nice RG studies to show that if the interaction strength is small, then the gap is stable, and you can still have Majorana states in presence of interactions. But but the implication of presence of strong zero mode is not just on the ground state manifold. It's actually, it has implication throughout the entire spectrum. So that's why, this paper, to show the implication throughout the entire spectrum, this paper came in 2013 that many body localization actually can make strong zero mode stable throughout the entire spectrum, and it can fight with interaction if you put a disorder to localize the degrees of freedom. And then people thought that strong zero mode may not be stable against interaction if you don't put a disorder to localize the degrees of freedom. But that expectation was wrong, because it was rigorously shown in this paper that even in XYZ Hamiltonian, which is genuinely interacting, I mean, it has quartic fermionic term, but even there is a perfectly normalizable strong zero mode, even in this interacting system, for a range of parameter values. The question was, what about non-integrable model? Because though XYZ system is interacting, its Bethe-Ansatz is integrable. So people also thought that maybe the existence of strong zero mode is connected to integrability, but it was never assumed in this paper. So that's why this question was always there, like, can you find a strong zero mode in a non-integrable system? Okay, so that's where our talk starts actually. So we will show that in locally driven system, you can have locally driven non-integrable system, you can see strong zero mode. So I will explain that. So the kind of Floquet phenomena that we will be focusing on in this talk is not that I described already, but it's the dynamic localization, which I will describe in brief. Then local driving, I will talk about local driving. I will show how strong zero mode emerges, and then I will also comment about the interesting entanglement structure of this system. So dynamic localization of single electron was predicted long ago in this paper, 1986. So for example, you just take a hopping Hamiltonian with an on-site term, and then you drive that periodically. You will see that the Floquet effective Hamiltonian is just like this, that this driving of this diagonal term is basically renormalizes this hopping strength according to this Bessel zero function. So this is periodic. So when this sin x goes to 0, the effective Hamiltonian is basically just switch off. So you do not have any hopping in the system. That's basically dynamic localization. And again, an important question was what happens in many body system, because this is for single electron. Then this paper came in 2010 by one of the organizer here, showing that that even in many body system, you can see exotic freezing of response. So for example, if you keep a magnet magnetic field, then the response of the magnet with respect to the magnetic field can freeze. If your magnetic field is time periodic, so the response of the magnet to the time periodic magnetic field can freeze at certain discrete frequencies, just like this thing. Okay, but then there is this nice review by Mukherjee et al. And Anatoli as well in this 2015 Advances in Physics paper. We did some work in Rydberg atom array described by PXP model, showing that we also have dynamic freezing, but only from one state, which is the vacuum state. And then there is also this interesting paper by Osmi Haldar et al. In 21 PRX, showing that emergent conservation laws is there to show the presence of dynamic freezing in this system. Okay, so I will talk about local driving. So these are all globally driven systems. So okay, and the model that we will consider is this staggered Heisenberg model. So you have this isotropic Heisenberg interaction, but staggered now, and you have a global field in the z direction. Okay, this model was actually studied long back in early 1990s, and the ground state of this system belongs to the Haldane phase of symmetry protected topological system, and this was also experimental. Some experimental realization was also found in some organic salt in these experiments. We now find that this was all ground state physics, but we now find the spectrum, this model is non-integrable. So if you look at the entire spectrum, then that's non-integrable. So this blue thing is H0, but if you put, if you don't give this staggering, which is just the Heisenberg model and field, which, but that's integrable, which is well known. But as soon as you put this staggering here, it becomes non-integrable, and so this GOE statistics. Okay. Now we will drive a certain set of this system, not all the spins, but a few selected spins according to this protocol. So this is just again a square pulse protocol. So you have, so this is the system. So this is the staggered interactions are here, and you have this global field on all the sites, and you are applying time periodic pulse only at a few sites. Okay. So if you look at the Floquet Hamiltonian, using Floquet Magnus expansion, if you expand in terms of this inverse of the drive amplitude, you will see that this zeroth order thing commutes with this SX1 operator for this choice of special choice of frequency, which is known as dynamical freezing. But when we perform exact numerics for nearly the same choice of parameters, we see that so here entanglement entropy of all the sites are plotted as a as a function of the drive cycle. So you see all other sites actually thermalizes quite quickly to the thermal value log2, but the boundary site it's not actually frozen. I mean, there is a finite relaxation of the boundary site as well. So of course this thing commutes with h of 0. The dynamic freezing is lost here. But another interesting feature is that if you increase the system size, then the relaxation gets slower. Yeah. So, okay, but what higher order says? So again, we find that the HF1, the next order is identically 0. And then HF2, we divide it into two parts, HF2 local and HF2 non-local. So local is any two-body term, just like the Bayer Hamilton. And two-body and one-body term, like the field terms. And non-local is anything other than that, like long-range two-body terms and three-body, four-body interaction terms, etc. So if you look at this HF2 local, then it has all sort of this 1 over gamma square, and 1 over gamma cube contribution. But this thing is special. This 1 over gamma term is usually not there for globally driven. This arises here only because of this local driving, because we are driving only the boundary site. So, and the HF0 is also of the order of 1 over gamma. So what you have to do, you have to take this and add with HF0 to get the renormalized Hamiltonian, which is correct up to 1 over gamma. And when we do that and construct this HF local by adding this term, 1 over gamma term here, so I am not mentioning the full expression of HF local, but you can visualize this schematically using this picture. So this is remain almost same as the undriven Hamiltonian. Only the interaction, these YY and ZZ interactions, and only this field are renormalized at the boundary side. So you see that the field is has been reduced to very small value, but it's not exactly 0. And the field is in the Z direction, so of course the SX1 will not commute with this thing. So, and you see that the SX1, the commutator of SX1 with even of the order of 1 over gamma, the local Floquet effective Hamiltonian is lost. So the boundary site is not even perturbatively frozen. So even on the leading order in perturbation theory, the conservation is lost. Okay, but if you add the higher order term like 1 over gamma square and 1 over gamma cube term, then so this 1 over gamma corrections are sufficient to show you the absence of freezing, which is also shown by this finite matrix element here, which is not 0. But when you add those 1 over gamma square and 1 over gamma cube terms, then you see perfect matching. I mean, so these terms are just required for quantitative better matching with the exact numerics. Okay, so the local terms seems are not enough. So we see relaxation, but it's slow. So we now ask the question from opposite angle that why this is slow. So you may think that these boundary fields and interactions are renormalized to very small value. So that may lead you to think that this is the mechanism of this slow relaxation, but that's an incomplete story, because when you do this calculation, so we have plotted SX1 and SX4 from exact numerics, and we have also done the same thing by just from the HF local. So you see that though this in the bulk of the system, which is SX4, site 4, it matches more or less well, but For the boundary side, the difference is a lot. So, so there are some other things, of course. So we ask the question that why the boundary relaxation is so slow. So the thing is, the zeroth order, the leading order Floquet effective Hamiltonian cannot explain this slow relaxation. So, okay, sorry for this ugly slide, but these terms, which are these non-local terms here, these are very important to give you this some suppression of relaxation, which we will demonstrate in this slide. So now, again, these exact plots are the same, but now when we incorporate those non-local terms in the Floquet Hamiltonian and do the evolution, now you see that both the bulk site as well as the boundary site now matches quite accurately with the exact numerics. So this might be a bit contradictory to what has been reported in this paper. So in this paper, they reported some experimentally observed deviation of from the dynamic freezing by constructing some accurate effective Hamiltonian. And also there is, like in today's previous talk, that some of us were wondering, like whether the dynamic freezing is stable against those higher order term. We would just like to point out here that the higher order term can even enhance the dynamic freezing in some cases, as we have found here. Okay, now the most optimal protocol, now we show the results for multi-site driving. So if you drive the sites, or this site, the SD is the set of driven sites. So if you drive in this sequence, then you see this surprisingly slow relaxation. The relaxation rates get suppressed exponentially. So, and when you just drive all the 4 sites in the system, then you see that it's perfectly flat. It doesn't evolve at all. And if you fix for a fixed SD and with increasing system size, again you see the relaxation gets slower. So, okay, and again so for multi-site driving, we have not been able to analytically calculate the Floquet Hamiltonian in higher order, but we just demonstrate that if you perform exact numerics and you you can calculate HF0, but not the higher order terms. But you can clearly see here that again, HF0 is not sufficient to capture the exact numerics here. And the exact numerics is actually flat, whereas the evolution governed by HF0, it just thermalizes quite quickly. So, yeah. Okay, so now I will argue that all these things is happening because of the emergence of a strong zero mode. You can translate this observation in terms of strong zero mode. The formal definition of strong zero mode is probably can be done with this properties. So you need to have a discrete symmetry operator in your system, which is this D operator here, let's say. And then you should have an operator xi, which is normalizable and anti-commutes with this discrete symmetry operator. Then xi should satisfy that the norm of the commutator of xi with the Hamiltonian reduced to 0 exponentially in system size. And one of the consequences is that the gap between the different eigenvalues gap between the energy eigenstates with different eigenvalues of D also goes to 0 exponentially. So these are the formal, this set of properties are the formal definition of strong zero. So now I will show that all these properties are satisfied in this system. So this is the Floquet Hamiltonian and the Floquet eigenstates. So let's assume that this is the discrete symmetry operator, which we show really is the case in this plot. That if you plot this expectation value of Bz in the Floquet eigenstates modulus and averaged over all the Floquet eigenstates as a function of drive frequency, then at these tuned values of drive frequency, you see that this dz is an emergent conserved quantity. Then since dz anti-commutes need to anti-commute with the strong zero mode, so we calculated the off-diagonal matrix element of this operator Sx1 in between different eigens, in between Floquet eigenstates with different eigenvalue of D, averaged over all the Floquet eigenstates that again approaches to this value half around this frequency. And most importantly, if you plot the average gap over all the Floquet eigenstates as a function of omega, you will see that there is an exponential drop of the gap at this drive frequencies. So yeah, so dz, of course, so dz is the emergent conserved quantity near this dynamic freezing frequency, and then all the other properties are also satisfied. Like if the gap is 0, then you can show that, I mean, if the gap goes to 0 exponentially, then the commutator will also goes to 0 exponentially. So okay, so now we have shown it here that for a fixed SD, the gap decreases a bit slowly, but if you fix the system size and this ND4 is the number of every fourth driven sites. So with this ND4, the gap actually, I mean, this shows a very nice exponential fit, the gap, and this is so we have fitted the value with this form. So the factor is like nearly 3. So this exponential drop of gap with system size as well as this ND4 is actually quite convincing to say that there is emergent strong zero mode here. And if you also calculate the matrix element of Sx1 in this Floquet eigenstates, then you also see that when you drive all the sites in this sequence, then this matrix element also approaches half, which is another requirement for the existence of strong zero mode. So all these just suggest that a strong zero mode emerges at this spatial choice of drive frequency, and also for the spatial sequence of driving. I mean, if you choose a different sequence, this does not work actually. So for example, if you would have taken like instead of 1.5, you could have taken 1.3, then actually the relaxation become even more faster. So this particular sequence is very important, which we still do not understand very well. We're just trying to understand that. Okay, now what about the entanglement structure of the corresponding Floquet eigenstates? So we find that this is a very interesting entanglement structure. So okay, so these columns are like the first column is for SD equals to 1 when you drive only the boundary site, and the second column is when you drive all the fourth sites in a fixed system site. And the first row is just the entanglement of the boundary site with the rest of the system. And the second row is entanglement of site 1, 5, 9, 13 with the rest of the system, I mean, according to this bipartisan. So you see that the boundary entanglement, I mean, when you go to this drive all the fourth sites, I mean, the entanglement of all the Floquet eigenstates saturates to the log2 value, which but if you look at the entanglement for these bipartisans, then it also, I mean, most of the eigenstates here still has a log2 entanglement, though these are just now the four sites. So this is just like the cat states. So cat state has log2 entanglement for all possible bipartisans. But so here the Floquet eigenstates are like cat state only for this specific bipartisans. So if you choose sites from this sequence, only then you will see the cat-like feature. But for other bipartisans, it's like ETH like behavior, which is, so this is a mixture of different kind of entanglement behavior like rainbow states, maybe. Okay, so okay, now I am already in the summary slide. So summary is there a strong zero mode in the system? So this is the non-integrable system. Okay, so we started with the non-integrable system. So our undriven part is a non-integrable model, and the locally driven models should be more chaotic. That's our expectation because it breaks symmetries, translation symmetries, though it has some more emergent symmetries, but maybe not sufficient to make the model integrable. So that's why we believe the driven model is also non-integrable. but you have a strong zero mode in a system. So now we have found a example where you see strong zero mode in a non-integrable model, which was a long-standing question. Only in this recent paper by Rakowski in PRB 2020, they reported this statistically localized integral of motions, which was probably the first prediction of strong zero mode in non-integrable system. But I would like to point out here that S-Liam, the boundary localized S-Liams are not literally same as the strong zero mode. They commute at any system size, not only in the thermodynamic limit. So they are not exactly same as the strong zero mode. So, but here we see that this locally driven system has all the traditional properties of a strong zero mode. So we believe that this is an example of a strong zero mode in non-integrable system. So our work was done in collaboration with Ron and Hitesh from Florida State University and Marcin and Arijit at UCL. So the work is already accepted in PRB. Thank you for your attention.
Okay, questions?
Is there any particular reason why you drive every fourth site and not third or fifth site?
We numerically found that those doesn't work. So for example, when you drive site 1 and 3, the relaxation become even more faster when you drive only site 1.
Okay.
Yeah.
More questions? Let me ask a very quick one. Yeah, I know about strong zero modes from Fenley's work, right? So there were these boundary spins, and you look at some autocorrelation functions at infinite temperature, and things don't relax to 0.
Yeah.
You see something similar here?
Yeah, okay. So we have not plotted the infinite temperature autocorrelator, but yeah, so okay. So I should have mentioned that. So okay, so this is like a huge file, so it's taking time. Okay, so in all these dynamics plot, the initial state is just the fully polarized X state. But we have checked that this remains same for all the choice of initial state in a fixed basis. So let's say X basis.
But it's just, it would be nice to just
sure,
actually
Absolutely.
calculate that.
Absolutely.
Okay, any other questions? Okay, if not, then let's thank Bhaskar again.
Thank you.